So far, we have used existing large language models as they are in our agentic AI systems. However, in many cases, it makes sense to think about making or improving the model itself for the specific task at hand. Sometimes the base model is simply too generic, not consistent enough in a niche domain, or not efficient enough for the environment where it will be deployed. For these situations, there are two important concepts worth briefly introducing in this video, helping us complete the picture of what is possible when designing agentic systems: fine-tuning and distillation. Fine-tuning allows a general-purpose model to learn from domain-specific examples, making it more aligned with a particular workflow style or policy. Distillation, on the other hand, extracts the behavior of a larger model and transfers it into a smaller, cheaper one, especially useful when building local or resource-constrained agents. In this video, we'll take a brief look at both approaches and how they fit into the broader toolkit. Let's begin. Fine-tuning is the process of taking a pre-trained LLM and training it further on a small domain-specific dataset. The goal is not to teach the model everything from scratch. That heavy lifting is already done during the large-scale pre-training. Instead, fine-tuning nudges the model toward a specific style, behavior, or domain. Fine-tuning is particularly useful when a model must follow a very specific tone or writing style, or when an agent needs reliable understanding of niche or domain-specific concepts, or when outputs must strictly follow certain rules, formats, or policies, or when a workflow demands predictable, low-variation behavior. Modern fine-tuning techniques typically require relatively small datasets, often a few thousand high-quality examples or even fewer, to deliver meaningful improvements for focused use cases. Fine-tuning builds on top of pre-trained LLM by adjusting its weights using a smaller focused dataset. Although the underlying optimization is similar to the original training, the scale is much smaller and the goal is more targeted. At a high level, the process has three steps. The first step is to start from a pre-trained base model. We begin with an existing LLM that already understands language, reasoning patterns, and general knowledge. The second step is to provide high-quality examples for a specific task. The model is shown input-output pairs, questions and answers, instructions and responses, or domain-specific conversations. Through training, it learns to mimic the structure, style, and reasoning found in these examples. And third, update the model's weights slightly. Instead of learning everything from scratch, the model makes small adjustments that shift its behavior toward the target domain or workflow. Because the model already knows general language, even a relatively small amount of data, sometimes just hundreds or a few thousand examples, can meaningfully shape its behavior. Modern LLM workflows rely on several techniques, each with different trade-offs in cost, data requirements, and control. Here are a few of the important ones. The first one is full fine-tuning, updating all weights. This is the classical approach. Every parameter in the model is updated using your dataset. It offers the highest flexibility and strongest specialization, but it is expensive and compute intensive. Today, it is used primarily in large-scale enterprise or research environments. The second one is parameter-efficient fine-tuning, or PEFT. PEFT methods update only a small subset of the model's weights, making fine-tuning dramatically cheaper and faster. The most widely adopted PEFT method is LoRA, low-rank adaptation, which adds small trainable matrices while keeping the original weights frozen. This makes it easy to produce multiple tailored variants of the same base model without retraining from scratch. And lastly, instruction fine-tuning. Instead of teaching new knowledge, this technique trains a model to follow instructions more reliably. It plays a major role in systems like ChatGPT. Instruction fine-tuning is especially valuable for agentic workflows that require consistent formatting, predictable behavior, and adherence to policies. Together, these techniques form the core toolbox for adapting LLMs to specialized agentic AI systems without restarting the entire training process. Distillation is another important technique for adapting large language models, but it works very differently from fine-tuning. Distillation transfers the behavior of a large, powerful model, which we call the teacher, into a smaller, more efficient model called the student in this context. In practice, the student is fine-tuned on examples generated by the teacher model rather than human-written data. The idea is simple but powerful. Instead of learning directly from humans, the student model learns to imitate the output, reasoning patterns, and style of a much stronger model. This allows the smaller model to acquire capabilities that would otherwise require large data sets or expensive training runs. Distillation is especially useful when the original model is too large or too slow to deploy. An on-device or local agent must run efficiently. Inference cost needs to be reduced while keeping behavior close to a high-end model. In other words, distillation provides and produces a lightweight model that behaves more like a heavyweight one, making it a valuable tool for agentic systems that must run fast, locally, and more cheaply. Distillation follows a simple teacher-student workflow. First, a large, high-quality model, the teacher, is prompted with many examples covering the tasks or behaviors we want the small model to learn. Second, the teacher generates answers, explanations, or reasoning traces. These outputs form a synthetic training dataset that captures the teacher's style and behavior. Third, a smaller student model is fine-tuned on this synthetic dataset, learning to imitate the teacher's responses even though it has far fewer parameters. Finally, the student model is evaluated and iterated, often repeating the teacher-student loop to gradually improve quality. This pipeline makes it possible to obtain a lightweight model that closely mirrors the behavior of a much stronger system, a practical advantage for agentic systems that need to run efficiently on local or resource-limited environments. In this video, we took a brief look at two important techniques for adapting LLMs for agentic AI systems, fine-tuning and distillation. We saw that fine-tuning allows a pre-trained model to learn domain-specific behaviors, follow instructions more reliably, and align to specialized workflows without needing to train a model from scratch. We also explored distillation, a method for transferring the behavior of a large teacher model into a smaller, more efficient student model, enabling faster, cheaper, and more local deployments. Together, these techniques expand the toolbox for shaping how an LLM behaves, making it possible to build agentic systems that are more accurate, more efficient, and better aligned with the tasks they are designed to perform.